Welcome to section 6.8 on indeterminate forms and L'Hopital's rule. In this section, we will learn about a new rule which would allow us to compute limits which we were not able to compute before using calculus 1 methods. For example, let's look at this limit. If we compute the limit of the numerator and denominator separately, we would get that the limit of 1 minus sine of x as x approaches pi over 2 from the left would be 1 minus sine of pi over 2 because sine is continuous everywhere and sine of pi over 2 is 1. So this limit is 0. The limit for the denominator is again, I can just put in pi over 2 into cosine because cosine is continuous at pi over 2 and cosine of pi over 2 is 0. This is a situation which we don't know how to compute using calculus 1 rules. Situation like this is called an indeterminate form of type 0, 0. It's called indeterminate because 0 over 0 does not make sense. This is just a symbol that we use to help us know what situation we're in. So here are some possibilities. If the function at the top, 1 minus sine of x, goes to 0 faster than the function at the bottom, then this question mark would be 0. If the function at the bottom, cosine of x, goes to 0 faster than the function at the top, then the question mark will be replaced by the infinity symbol. But often there is a compromise where the answer is a non-zero number. We cannot tell which situation we're in. In the next slide, I will talk about a method which will allow us to determine which situation we're in and compute this limit exactly. This is called L'Hopital's rule. And this method works when you have two functions, f and g, and the two functions are differentiable. And suppose you know that the limit of f is 0 and the limit of g is 0. And you also know that you can compute the limit of f prime over g prime. When these conditions hold, then we have this equality where the limit of f over g is the same as the limit of f prime over g prime. We can also replace the symbol with the limit as x approaches a from the right, or the limit as x approaches a from the left. You can also replace a with the infinity symbol or the negative infinity symbol. So in our example, we have already computed the limit of the top function to be 0 and the limit of the bottom function to be 0. And these two functions are also differentiable. So we can attempt to apply L'Hopital's rule. And 0, 0 tells us that these two limits are 0. So here you can think of f as 1 over sine x and g as cosine x. And what I do is I write down the quotient. So I write 1 minus sine of x over cosine of x. And I'm hoping to use L'Hopital's rule. So let me write down d dx of 1 minus sine of x and d dx of cosine of x. In the next step, I compute the derivative. So I have negative cosine x over negative sine x. And let me simplify this. So I have cosine x over sine x. And I see that if I were to take the limit of cosine x as x approaches pi over 2 from the left, this is the same as cosine pi over 2. And if I take the limit as x approaches pi over 2 from the left of sine of x, I would get cosine, I would get sine of pi over 2, which is 1. So this last value is 0 over 1, which is 0. And now what I will do is remember that I'm allowed to do this part here, where if two of the numbers are defined, I'm allowed to have this equality. And I write down the limit for all of the other values. And the most important step here is this first equality. The equality holds by L'Hopital's rule. 0, 0. And so we had just computed that this quantity is equal to 0. We were not able to compute this before L'Hopital's rule. In this section, there are only 2 theorems, and this is the second one. Basically, you will replace the 0 here with infinity. It could be plus or minus. And if the right-hand side exists or is infinity or negative infinity, then this equality holds. So let's practice doing that with this example. So first, I need to check that these two conditions hold. So I take the limit as x goes to infinity of natural log. And I see from the graph it is infinity. And I also compute the limit for square root of x. And I know it is infinity. I can make square root of x as large as I want. And again, if natural log wins, the answer to this question is infinity. If square root wins, the answer is 0. And if there's a compromise, the answer would be in between. So it would be a positive number. In this particular example, we have done some data for this, suggesting that natural log grows much slower than square root of x. So we think that square root of x should win. And so we think the answer should be 0. But usually we will work with functions where we don't have any data, but we can compute the limit using L'Hopital's rule. This quantity is called an indeterminate form of type infinity infinity. Now, this symbol doesn't make sense as a quantity, but this is just a symbol to help us remember what situation we're in. So we're in a situation where the limit of the top function is positive or negative infinity, and also the bottom function approaches positive or negative infinity. And we cannot compute the limit directly, so we can try to use L'Hopital's rule. I again start with writing down the quotient, so natural log of x and square root of x. And because I know I'm trying to apply L'Hopital's rule, I will write down the derivative of the numerator over the derivative of the denominator. The derivative of natural log is 1 over x, and the derivative of square root is 1/2 x to the negative 1/2. And I simplify this. So I bring down, so 1 over 1/2 is 2. And then 1 over x to the negative 1/2 is the same as x to the 1/2. So this becomes 2 over square root of x. And this is good because now I know how to compute this, because the denominator can be made as large as we want as x goes to infinity, and then the numerator does not change. We can make this value as small as we want by making x big enough. So this is equal to 0. And in fact, this is our answer, but let's finish explaining why we had just used L'Hopital's rule. So I write down all of the limits. I want to now explain that I have used L'Hopital's rule. So the first equality is due to L'Hopital's rule. And we want to remind ourselves that this is of type infinity infinity because of this computation. So it's important to do this check. Otherwise, sometimes you might just blindly use L'Hopital's rule and accidentally get a wrong answer that way. I have explained both L'Hopital's rules, but now we can have different situations where we have to do certain things before we can apply L'Hopital's rule. So the first type of example where we might have to change the function a little bit or change how it looks like is called of type infinity minus infinity. So in this example, I have limit of secant x minus tangent of x. Now let me first compute the limit of each function separately. So secant is 1 over cosine of x. And this is the graph of cosine. And as cosine approaches pi over 2, it approaches 0 from the left. And so if you're approaching pi over 2 from the left of 1 over cosine of x, that means you can make this denominator be as small as you want. And so the whole thing can be made as big as you want. So the symbol is positive infinity. Next, I can compute this limit. I can draw the graph for tangent. And as we approach pi over 2 from the left, tangent of x approaches positive infinity. So just by looking at this, we don't know what's going to happen. If secant x dominates, then the answer would be positive infinity. But if tangent of x dominates, then the answer would be negative infinity. And if neither of them dominates, then there would be a compromise where the answer would be a number. So one method that works is to first convert this difference into a quotient. A quotient is a function over another function. So let me rewrite these in terms of sine and cosine. So secant is 1 over cosine. Tangent is sine over cosine. So I have 1 minus sine of x over cosine of x. And now we are in a situation where we can try to apply L'Hopital's rule. So we check the limit of the top function. And this is 0. And then the limit of the bottom function is also 0. So this tells us that we can try to apply L'Hopital's rule for the 0, 0. And in fact, we already did it at the beginning of this lecture. So if we had not done this already, then we would go ahead and done this whole thing that I did earlier and got that the answer is 0. So in general, whenever you have a situation where you're trying to compute the limit of a difference, and if you compute the limit separately, you have infinity and infinity, then you wouldn't know what to do directly, but you can try to apply L'Hopital's rule. But first, you have to turn the difference into a quotient, something that looks like a function over another function. And then once you do that, you would try to apply L'Hopital's rule. So it's going to be either the 0, 0 or infinity, infinity. Next, we have another situation that is called of type 0, infinity. We're not going to learn a new rule for this because what we will do is turn the situation into a situation where we can use L'Hopital's rule, either 0, 0 or infinity, infinity. But first, let me give you a warning. So let's look at this statement. It says that if you compute the limit of a function to be 0, and you see that another function g approaches infinity, then the limit of the product is equal to 0. This statement is false. And you should be able to find a counterexample where you have these two conditions to be true, but this limit actually is either infinity or a number that is not 0. So this is not true. And but that is why you want to be careful in this situation, and you have to use L'Hopital's rule to figure out this limit. Now let's look at what we have. So we have a product, and we're trying to compute its limit as x approaches 0 from the right. So first we compute the limit of each function separately. X squared goes to 0, and the natural log goes to negative infinity as x approaches 0 from the right. If square root of x is more dominant, then this limit will be 0. And if natural log is more dominant, the answer is going to be negative infinity. But often there's a compromise, and the answer would be a non-zero number. And what we have to do is first turn this product into a quotient. What you can do is either keep this square root of x alone, but replace natural log of x with 1 over natural log. Or you can leave natural log alone and replace square root with 1 over square root of x. Now let's first try the first one. So now my top function is square root of x, and my bottom function is 1 over natural log of x. And I check that the limit for both are 0, so we can attempt to use L'Hopital's rule. So let me write down first the quotient, and then I want to compute the derivative of the top over the derivative of the bottom. So I get 1/2 x to the negative 1/2 over negative 1 over natural log squared times 1 over x. And if I simplify, I get negative 1/2 square root of x times natural log squared. But this is even more complicated than the expression we started with. In general, we want things to be less complicated after we apply L'Hopital's rule. So maybe our first choice is not a good choice. So let's try writing our product as this other quotient. So now I'll write my product as this quotient. And now my top function is natural log of x, and my bottom function is 1 over square root of x. I compute that the top function approaches negative infinity and the bottom function approaches infinity. This means that we can attempt to use L'Hopital's rule infinity over infinity. So let's try. So first I write down the quotient, and I compute the derivative of the top function over the derivative of the bottom function. The derivative of natural log is 1 over x, and the derivative of the bottom function is negative 1/2 x to the negative 3/2. And let me simplify this a little bit. So let me rewrite 1 over x as x to the negative 1, and the bottom as 1/2 negative 1/2 times x to the negative 3 over 2, and this will be negative 2 times x to the 3/2 minus 1. So I have negative 2 to the x to the 1/2, so that's the same as square root. And now I know how to compute this limit. So the limit as x approaches 0 from the right of the square root function is 0. So that multiplied by -2 is still 0. And now I write down all of the limit from the beginning. And the part where we will use L'Hopital's rule is this first equality. And you can practice similar questions over here. Now, let's look at this limit. If we were to try to apply L'Hopital's rule, we would compute that the limit as x approaches pi from the right would be 0. And then the limit as x approaches pi from the left of cosine of x would be 1 minus cosine of pi, which is -1. So this is 2. So this is not 0. So this means we cannot apply L'Hopital's rule. But we can use calculus 1 rules. So we can simply put in pi into the sine of x and cosine of x, because sine of x and 1 minus cosine of x is continuous at pi. So then I will just have 0 over 2, which is 0. So that is this limit. And if you had tried to use L'Hopital's rule without checking the condition, you would have gotten a different answer, which is not 0. Finally, we have 3 more types of indeterminate forms. It happens when you have the limit of a function to the power of another function. One situation is where f goes to 0 and the exponent also goes to 0. This is called type 0, 0. We wouldn't know exactly what the limit would be without doing more computation. Another situation is where f approaches infinity and the exponent approaches 0, and we don't know exactly what it would be. The last one might be a tricky one, because you see that the limit of f is 1 and the exponent approaches positive or negative infinity. And you might think that the limit should just be 1 because f approaches 1, but this is not true. This is an indeterminate form of type 1 infinity, and we need to do more computation before we can compute the limit. But here is a strategy that works for all 3 types of indeterminate powers. First, you write down just the function and set it equal to y. And then you take the natural log of both sides. And we will bring g down here. So now we have g times the natural log of f. And what will happen now is that for all of these types, then if you can look at the limit of the natural log of y, and this will be an indeterminate form. Of type either 0, 0 or infinity, infinity. And from there, we can use the L'Hopital's rule. And once we compute this limit, we can then compute the limit for y by just taking e to the limit. So let's do an example. So here I have this function to this function, and I want to know the limit. And I try to compute this directly without using L'Hopital's rule, but I see that the limit of 1 plus x as x approaches 0 is just 1. Just plug in the 0 to x. And the limit of 1 over x as x approaches 0 is positive infinity. So this is an indeterminate form. It's not true that this is not equal to 1. This is an indeterminate form of type 1 infinity. And so we will apply the technique that I mentioned in the previous slide. So I write down y equals the function I am interested in, and I take the natural log of both sides. The right-hand side becomes 1 over x times natural log of 1 plus x. So now instead of working with this power, we can work with this function instead. This is already in a quotient. It's natural log of 1 plus x divided by x. So let's compute the limit of the top function. So that is natural log of 1 plus x. And this is just natural log of 1, which is 0. And then the limit of the bottom function is the limit as x approaches 0 from the right of x. This is just 0. So this means we can try L'Hopital's rule of type 0, 0. So then I write down the function. And then I write down the derivative of the top function. And then the derivative of the bottom function. So the derivative of the top function is 1 over 1 plus x. The derivative of the bottom function is 1. And this is good because I know how to compute the limit of 1 over 1 plus x as x approaches 0 from the right. I can just plug in 0 into this x, and this is 1. And now I just write down the limit symbol for all of the other values. And the first equality is where I apply L'Hopital's rule. So I'm almost done, but not quite. So I have computed the limit for the natural log of y. So let me compute the limit of what I want, which is the limit of this function, but we have already set this function to be y. Actually, let me write down the whole thing. So the limit of 1 over 1, the limit of 1 plus x to the 1 over x as x approaches 0 is the same as if I replace this whole thing with y. And now let me replace y with e to the natural log of y. And e is continuous everywhere, or e to the x is continuous everywhere. So this is equal to e to the limit of the natural log of y, which we had already computed. So we have e to the 1. E to the 1 is just the number e. So this limit is equal to e. And in fact, this is one of the definitions of e that, depending on what book you're using, might be the definition instead of the definition that we use. In summary, this is what we have learned so far. So first, try to compute the limit using calculus 1. But sometimes it doesn't work. So if it doesn't work, try to write the function as a quotient, so f over g, and then check that either both f and g go to 0, or both f and g approach infinity or negative infinity. And if one of these holds, then you can try L'Hopital's rule. And you might also be in a situation where you have the limit of powers. If it's possible to not use L'Hopital's rule, then you do it. But if they are of the situation where f goes to 0 and g goes to 0, so that's the 0, 0 type, or if you have the situation where f approaches infinity and g approaches 0, then it is this indeterminate form. Or if f approaches 1 and g approaches infinity, this is also an indeterminate form. Be careful, the answer is not going to be 1 usually. So whenever you have this situation, you can just write down the function as y, and then take the natural log of y. And this is going to be something that you can then compute using L'Hopital's rule. And once you've done, your answer is going to be e to the limit that you compute, like I did in the previous slide. So in general, there are situations where you cannot do methods from calculus 1 or L'Hopital's rule, but in this section and in this class, we will be working with situations where you can either use calculus 1 or you can use L'Hopital's rule.